Hi, and welcome to this video where we're looking at equations of motion again, but this time we are talking about variable acceleration. Previously you've seen the SUVAT equations, and the key thing for using the SUVAT equations is that acceleration is constant. When you get variable acceleration, i.e. the acceleration changes as we go through time, then the SUVAT equations no longer apply, so we need a different way of dealing with things. So we're going to have a look at how that affects a velocity time graph and what it looks like on a velocity time graph. We're going to have a look at how we can use equations for displacement, velocity and acceleration as a function of time, and then at the end of it we are going to get into some calculus and see how the calculus, i.e. the differentiation, the integration you've done on the pure side of the course, can be applied to this side as part of the mechanics. Okay, so let's crack on. First of all, let's just have a little look at the graphs and look at defining some motion in terms of a function of time. So here we go. So there's our standard velocity time graph. When you've got constant acceleration, clearly it's a straight line because acceleration is the gradient of the line. However, if acceleration isn't constant, what you get is a curve. So something like this, what we've got is quite a shallow gradient here, which means it's accelerating, but the rate of acceleration is not particularly high. But then as the curve gets steeper, we're saying the change in velocity over change in time changes, it gets steeper, so acceleration is increasing. Right. And let's say rather than working with SUVAT, we're going to be looking at how we can express this kind of relationship as a relationship in terms of linking velocity and time together via an equation. So here we go. So what you've got is a car moving along the track, and we are given the fact that this equation is being modelled, the motion is being modelled by this equation: s equals 2t cubed minus 14t squared plus 20t, where t is time after the start of the motion, and s clearly is displacement. You're never really going to have to come up with these equations yourself. In the exam you're always going to be given these things, so don't worry about trying to create your own versions of these. They will always be given to you. So here we go. So first thing I'm going to do is have a look at what that looks like on a displacement time graph, which essentially means we're going to have to plot this cubic. So first I'm going to do is find the intercepts. So when t equals 0, our s-intercept is 0, so it starts at 0. And then for our t-intercept, which is going to be the horizontal axis, which is equivalent to the x-intercept, we're going to put s equals to 0 and do some solving. Clearly that we can do a bit of factorising on it, take out 2t, factorise the brackets there. We've got our two brackets, t minus 2, t minus 5, and that gives us 3 solutions. And so that gives us enough to be able to plot the cubic curve, which looks like that. We've got intercepts at 0, 2, and 5. So that's the motion of the particle in terms of how far away it is from its starting point at any given point in time. So what we're going to do is have a look at what this motion looks like in terms of, there's my little car who's going to move along this line. So what we've got is the car starting off when t equals 0, and it's going to start up by moving in the positive direction until it reaches point x. Now, where is point x on the graph? It's the point at which the displacement, the positive displacement, is furthest away from the origin. So that's going to be this point here. So point x. We can also see at that point what's happening is, if this is displacement, at this point here, if you think about your calculus, we've got a turning point. So that's when ds dt, change in displacement over change in time, is 0, i.e. the velocity is 0. So effectively what's happening is it's accelerated away, and then it's slowed down again, and it's come to a stop. At which point, this section of the graph here, what the car's doing is moving back towards the origin. So essentially it turns around and moves back there. And now we're back at the origin when t equals 2, so at this point here on the graph. Now, I know my graphic has stopped, but in reality the car doesn't stop there, it just keeps on going. And now we're into negative displacement, so we're the other side of the origin. And clearly we're now at this point y, and that is the furthest negative displacement, so that's going to be that minimum point on the curve there. At which point again it's kind of been accelerating from x, and then it gets to here, it slows down, instantaneously comes to rest, at which point it's now going to go back the other way, and it's going to return. So this section graph here is when the displacement is getting closer towards the origin again. So it turns around, travels back to there, so now we're back at the origin again there. And then the final section of motion is off, the displacement is positive, and it just disappears off in that direction. There it goes. So what we've got is that motion. So what we need to understand from our graph is what we've got here is positive displacement. Down here we've got negative displacement. And essentially what's happening is this car is just moving backwards and forwards along a straight line. Now clearly this is a cubic, and the cubic graph will now just disappear off and get steeper and steeper and steeper and disappear off the top up here, which clearly is not relevant because something cannot accelerate and keep accelerating forever. So what you normally find is there's limits placed on these things, i.e. the model only applies for a certain section of the motion. So it might be that this equation here is only suitable for describing the car up to maybe about 6 seconds. Okay, so there we go. So that's what's going on with the motion. Let's now do some calculations using this. So it says find the displacement of the car when t equals 6. That's a fairly straightforward calculation. So we know t equals 6. We're just going to plug it into there. And so we've got s equals 2 times 6 cubed minus 14 times 6 squared, 20 times 6. Substitute the 6 in, do the working out. So at t equals 6, we're over here on the graph, and the car is now 48 metres away from where it started. Now, that's not to say that it's travelled a total of 48 metres, but it's just saying it's 48 metres in the positive direction away from where it started. This is the other part of the question, so like the total distance travelled. So this would be, imagine like the car, we said it went that way, and then it went back this way, and then it went off the other way. So we've got to figure out how far it's travelled in total. So what we're going to need to do is to find the displacement. How far away from the origin am I when I'm at point X? How far away from the origin are we when we're at point Y? And so these are the maximum and minimum displacements, and I mentioned this earlier. So what we're talking about is max and minimum displacement. We're talking about doing some differentiating to find the turning points. So here we go, ds dt. We're going to differentiate our equation. Excuse me. So that gives us 6t squared minus 28t plus 20. The maximum and minimum points are going to be when ds dt equals 0. As we can see from these points here, our turning points. And stick it equal to 0. And do some solving, and again I've done the solving just by whacking it into my calculator, and we get that value there for t. Not a particularly nice value, but it basically tells us that the two values. So when t is the positive version, we're going to get the furthest point away, so that's going to be y, so that's going to be that one there, and s minus 16.4. We expected that to be negative because it's below the axis, and so that's the displacement of y. And then for our other value, 7 minus 19 root 19 over 3, that's going to be x. So x is 8.12 metres away. So all I've done here is found out a value of t, and then taken this value of t, again left on the calculator screen, just plugged it back into there. Doing this kind of calculation when the numbers are not particularly nice is where having the A and S key on your calculator makes it a whole lot easier, and also avoids any kind of rounding error. So now we know how far away x is from the origin, we know how far away y is, but we've still got to think very carefully about how far it's travelled in total, because to go from 0 to x and again back to the origin, obviously the car has travelled 2 times that value. Likewise with y, so our total distance travelled is 2 times from 0 to x and back, 2 times from 0 to y and back, so we've gone to x, come back, we've gone to y, come back, and then we've got the final bit up to the 6th second, which we had from the previous part, which was 48 metres. So there's our total distance travelled, which is a total of 97 metres.